ma per il momento, a parte le trasmutazioni sul filo, di emissioni di neutroni e gamma non ne abbiamo viste. Diciamo che nella zona bassa energia non abbiamo una buona risoluzione con lo ioduro di sodio, per cui col multicanale a ioduro, però potrebbe esserci qualcosa lì, ma sarebbe comunque poca roba. Ecco, qui invece vedete una serie di esperimenti, comprese le curve di calibrazione, in cui si nota che ad una certa temperatura rispetto alla linea di calibrazione, che è quella linea sottile bianca che vedete nella parte superiore del grafico, ci sono episodi di produzione di eccesso di potenza che vengono misurati come variazione della temperatura della camera del reattore, sottraendo ovviamente le variazioni della temperatura ambiente. Si vede che questo comincia intorno ai 120 gradi, come faceva vedere prima Francesco, e dove si ha l'inizio veramente un pochettino dopo, sui 150-170 gradi, l'inizio dell'assorbimento da parte del filo di costantana dell'idrogeno. In qualche caso, diciamo a 300 gradi, questo il picco maggiore che abbiamo ottenuto è questo qui a 300 gradi di circa 2 watt, però parliamo di 50 milligrammi di materiale, quindi diciamo la quantità in proporzione al materiale potrebbe essere significativa, e c'è la linea dell'errore qui che è intorno ai 200 milliwatt. Questo è l'errore calcolato come variazioni minime e massime dell'escursione della temperatura del reattore con le curve di calibrazione. Abbiamo usato le varie curve di calibrazione per stabilire l'entità dell'errore. C'è da dire che anche fili di costantana messi all'interno del reattore, sempre sulla stessa piastrina depositata sul riscaldatore, tutte le prove sono fatte con riscaldamento indiretto, senza far passare corrente nel filo, e abbiamo visto anche esperimenti senza produzione di calore. Quindi c'è sempre la domanda: come mai un filo una volta si produce, una volta non produce? Perché produce soltanto in quelle zone alterate e non tutta la superficie? Questo è un pochettino un interrogativo che si pongono, penso, tutti gli sperimentatori in questa materia. Questo è il riassunto a parole della chart precedente, quindi ve l'ho già fatto e lo posso saltare, giusto?
Vai.
Ecco, questo invece è un esperimento fatto con un reattore nuovo, dove c'è la possibilità di arrivare a temperature più alte, un reattore molto più leggero di quello che avete visto nelle foto, quindi è fatto proprio come una lattina di Coca-Cola, molto più snello, e quindi per riscaldare l'interno serve molta meno potenza. E qui vedete che fino a 200 gradi, diciamo, un filo di costantana, in questo caso più lungo però, non 25 centimetri ma 2 metri di filo, e praticamente la temperatura del reattore serve una curva a potenza nulla. Abbiamo usato il primo tratto come curva di calibrazione. All'improvviso, diciamo intorno ai 220-230 gradi, c'è una discontinuità che non è spiegabile da un comportamento anomalo del reattore, e si vede che c'è una possibile produzione di energia. Con lo stesso reattore sono riuscito ad arrivare fino a 450 gradi e si arriva sugli 8 watt. Si arriva sugli 8 watt con una potenza in ingresso inferiore ai 30 watt. Quindi, diciamo, dal punto di vista energetico è un valore con 400 milligrammi di materiale. Quindi è interessante. Su questo reattore qui dobbiamo fare però delle verifiche, perché abbiamo fatto pochi esperimenti. Questa è l'ultima chart, vi ringrazio per l'attenzione.
Io pregherei Yogi di
fare da diciamo, un po' di traduzione perché è argomento delicato, tu sei la persona più indicata.
Professor Guida della Northwestern University di Boston, uno dei più importanti fisici teorici in circolazione. Prego.
I'm always embarrassed because the other two members of our theoretical group, Professor Sebastian,
You can sit down. Sit down. Sit down.
the other two members of our group, Professor Swain and Professor Sebastian, could give this talk in maybe 10 different languages, including Italian. And I'm always very embarrassed that of the three of us, I'm illiterate of your very beautiful language. So I apologize about giving this in English.
Ma parla in inglese che non capisco.
Sì, ha detto parla in inglese, poi lui ci darà una...
No, io faccio un patto. Se lui dice qualcosa che non avete capito, io tenterò di tradurre il massimo, se no continuous translation è un po' difficile, giusto? Perché non sono un professionista.
Okay. Shown above or there is what one of these water plasma batteries look like. There's the picture, there's the light. This particular one is used for electroplating atoms from solution onto metal plates. But the plasma glows, and if you look at Fleischmann's batteries, one particularly before it exploded, it glowed like that. And if you look at some of the recent from Milan things, that thing also can explode if they're not careful about when they heat it. But they look like that. So the first thing, without any mathematics, although I claim to be a theorist, is that they glow. They're very bright. So I'm going to first describe chemical cells. One of the original chemical cells where they saw transmutations is due to Mizuno. This is actually called a Mizuno cell. And it's not glowing very strongly, but you can see it glow. This one is part of a Naples group, Cirillo et al. And these are pictures of their apparatus, which is a Mizuno cell. And you can see that when you put a voltage across it, first, it just stands there. Secondly, the water begins to boil, but that's not when the transmutations take place. And thirdly, it creates a water plasma, and there's the picture of the water plasma, and it glows. Just keep that in mind. So again, when their cell, and this is the Naples group cell whose photographs I'm using, when that thing starts doing transmutations, it lights up the room. So sometimes in a graph, one doesn't appreciate that. And the other thing that one should appreciate is that there are so many transmutations that you can see the new chemicals with your eye. I'm going to talk about another experiment in Torino that I was happy to witness at the Polytechnic University there, where again, you can see the transmutations with your eye. We hear a lot about people having trouble seeing the transmutations. Well, you can do this or that chemical analysis, but if you look at that, you can see it with your eye. So one is that it glows, and two, you can see the transmutations. A lot of different chemicals that weren't there with your eye. These are large amounts. The people that can only see trace amounts seem to be, well, they seem to be at conferences such as this to tell you that what they're working on doesn't happen. again, you can see with your eye along the electrode where the different elements are forming. And when you look at the surface of it, you can see slivers of where the new elements are forming with your eye. And if you look at the tip of it, it's all scratched up. It's all indented because there have been little nuclear explosions going on in there. And if there are nuclear explosions going on there, the idea of seeing it in a nice crystal is crazy. So they explode. They deposit plenty of transmutation materials. There are enough groups that have seen this that I would say you have to be blind not to. And, of course, there are neutrons being detected. The neutrons being detected here happen to be rather slow, in my opinion. But in other experiments that I'll talk about, by slow I mean thermal neutrons or less energetic. But there are some fast ones in experiments that I will discuss at as high as 20, 25 MeV. So we had a theory for a long time about weak interactions giving you the neutrons. So what would happen there is that an electron and a proton would meet. There's no barrier. Electrons negative, protons positive, they like to get together. And if the proton can capture it, then you get a neutron plus a neutrino. And there are cross-sections for this that are well known. Actually, I'm going to give you a rather crude model where these things are just take place two bodies at a time. This crude model is due to the Rona group, not to us, but I'm going to stay with it for a while. That you can just describe this in terms of particles interacting two at a time. The actual case is there's a plasma oscillation. So you might have 1 million electrons going back and forth. And although only one of those electrons will knock off a proton, many electrons in the collective going back and forth actually contribute to what the process is. But in the simplified, and I think oversimplified model, you just take the particles two at a time, in which case you get a cross-section which depends on the wave function, two-body wave function of the electron and the proton being on top of each other. And you can work out two cases. Well, first of all, this is if you have these electrons moving in an oscillating electromagnetic field, which is coming from the plasma, these electrons get a mass enhancement. I write a few formulas because I advertise myself as a theorist, and I'll try to get back to pictures as quickly as possible. Not quickly enough. This is the simplified gas model. These are how you calculate the wave functions. And here's the one where we're back to pictures. I want to stay with this. In the Rona group, Mayani and co-workers, they used a two-body wave function in which the electron and the positron were bound. And in picture terms, that would correspond to this case where there's no plasma. For the fully ionized plasma, the electron-proton wave function has to be two that scatter off each other. And then you're in that regime, and the two results differ by a factor of about 300. And and that's why I show the pictures, since these batteries glow in the dark, you're not supposed to use the one where they're bound and they don't glow in the dark. And I believe that was the main difference of opinion between the Rona group and ourselves. The conclusions to this part is that first on the bottom, when these transmutations take place, they light up the room. They take place in the water plasma. Water plasmas are well known in a lot of industrial applications. And second is you can see it with your eye. You also have to do the chemical analysis to make it precise, but it's just blindingly obvious. Whoops. That's not the end.
Forse,
got it.
forse scusa, se questo punto qui che è un punto anche di polemica delicata.
Ok, ok. Beh, polemica dovrei fare io. Il punto principale, differenza fra il gruppo di Roma, Magliani e Company e noi, che loro hanno usato il caso dove elettrone e protone sono bound state, sono legati, così se pensiamo io ce l'ho un gas di atomo di idrogeno che non ce la carica. Invece quando c'è un plasma dove elettroni e protoni sono separati, so charge plasma, not neutral plasma, a quel punto il nostro conto è per il plasma, il loro è per un neutral hydrogen gas. E infatti questa è la differenza. Ma l'esperimentale, come lui ha discusso, vale quando c'è il plasma. Infatti la produzione di neutroni e anche per le trasmutazioni servono plasma. It's a collective effect, it's not one by one. Okay? Vabbè, vai.
I'm now going to switch subjects to piezoelectrics. Yogi covered a lot of this ground this morning, and there's just a picture of quartz, which is the one of the best examples of piezoelectric crystals. We'll discuss a lot of things, including how rocks crack and stuff like that.
This one.
That's what I pressed.
Bisogna cliccare col mouse sulla freccina.
Okay, in my version, this thing isn't moving, but a piezoelectric is when you squeeze it, the voltmeter changes. In the PowerPoint, for reasons I can't figure out, it moves. The other thing is, I stopped smoking a long time ago, among my other unhealthy habits. But these piezoelectrics create a spark, and the spark starts a flame, and so this has industrial purposes. And the other one that Yogi had discussed was kids bouncing up and down on sneakers, which will give you flashing lights, which is healthier than the cigarette lighter. Also, if you have a cheap watch, here's an example of a cheap watch. That's what's inside it, making it go tick-tock, is again the piezoelectric crystal. Here's another piezoelectric giving you a cigarette lighter, except it's an earthquake. So here you really start crunching the rocks. And this was taken by, not a professional. It was taken by a Japanese citizen, and it's well known that the Japanese like carrying around gadgets where they can take pictures when they see anything interesting. And he saw lights that were interesting during an earthquake, and a lot of people don't believe it. You can forge a photograph, but there'd be no point to it, so I believe it. And in fact, Japanese who observed a lot of earthquakes see these lights. The Chinese also see these lights. I guess they like gadgets these days also. And this is a picture during an earthquake, but it's not professional, where you see the light in the sky being given off in an earthquake regime, and if you wait around till night, it's still there. But again, this was not professional, so people don't believe it. This is the recent tragic earthquake in L'Aquila, and this picture is finally professional. What I mean by professional is that the European Space Agency took these pictures from a satellite, and if you look in that region during the earthquake tragedy, you see these earthquake lights, which the Japanese and the Chinese have been telling us for years are there, and they were there. And so you get a lot of light from earthquakes. You get a lot of light from earthquakes because crunching stones gives you a lot of radiation, very powerful radiation. They're also very light. So crunching stones in an earthquake sounds terrible because you hear the rocks crunching. And when you hear the rocks crunching, they seem to crunch in two kinds of waves, S waves and P waves that have nothing to do with what a physicist calls S waves and P waves. S stands for shear and P stands for compression. And the compression wave is faster than the shear wave, which is why when you get a big crunch and you see the seismic reading, the compressional wave, they call P, comes first, and the shear wave comes second. And this is observed everywhere around the Earth. When you finally get enough of this sound and enough of this light coming from the crunching of little cracks, they go into a big crack, and that's what the results of the earthquake looks like. And here at the Polytechnic in Torino, they got a little machine that'll cause a mini earthquake. You take granite, which has quartz in it, and you put it in this machine, and you crunch it. And when it crunches, this is what it looks like after the crunch, you have some big cracks, which is a mini earthquake. They find neutrons firing out of it. Now, I just really learned about these experiments a month ago, about a month ago. And Yogi and I had visited Torino, and they gave us a demonstration. And they said one thing which really surprised me. They said, you can convert iron into 2 aluminums plus a couple of fast neutrons. And my answer to them is I thought they were crazy, because that's fission. And I don't like the word cold fusion, but if I had to call this something, I would call it cold fission. They were getting fission events by crunching rocks. And I read in the literature that they only had this kind of hospital-like neutron detector, but no, they have 3 detectors. They have a bubble chamber detector, they have the usual high-energy helium-3 detectors, and they're seeing neutrons. Lots of neutrons. Lots of chemists are saying, how do you know they're seeing neutrons? Well, everybody else using those equipment that sees neutrons, I mean, that's the way nuclear physicists have been measuring neutrons. I was also told that there's so much iron being converted to aluminum that if you take one of the chips, you can very often see the splotch of aluminum with your eye, just like the cell. And they gave us a demonstration, so I said, if I pick up a chip, am I going to see an aluminum splotch on it? And they said, well, that's a probabilistic question. Why don't you pick one up? So I picked up a chip, and I looked at it. My eyes are, I'm 72 now. My eyes are a little shaky, but I saw it pretty clearly. So you can see it with your eye. The neutrons are plentiful. There is not the slightest doubt that this is what's happening. The only trouble was with Yogi and myself, and John Swain, who didn't come to a day or so later, we had no reason for why it was that crunching a rock would induce a fission which required energy. And so we were asked whether we could explain it, and our answer was not in a day. It would require more than a day. Maybe it's because there were 3 of us. I think we got the essence of it in about a week and a half. So I think we understand it, and it's spectacular in what it applies. This is the group in Torino. This is another case of crunching rocks. This is called fracking by people who don't like it. You dig straight down. You dig straight. This is, by the way, how the United States is going to get over being dependent.
Shale gas. Shale gas. See, fracking.
Right, fracking, yes. And again, as a matter of crunching rocks, this is how the U.S. plans on getting independent of Saudi Arabian oil. And so what they do is they go down, and you need to measure how deep are you. When do you finally hit the granite, which is piezoelectric. And the way they do that is they download down the pipe radiation detectors. And a lot of this stone has been crunched around before, and they each have a different radiation signal. And I believe that's largely due to the difference in the rocks that have been crunched. When they get down to the granite, they see many neutrons and so forth, and they say that's just the way the granite is. But I think that's an oversimplification. When they see the appropriate nuclear radiation, they make a right turn. And then they go like that. And then you pour this rancid water down that pipe, through there, and the rancid water is sitting in that pipe, and you put so much pressure on the rancid water that it goes up into the shell and it cracks it. That's fracking. So you hear the sound, you get the light. I'm sure you get nuclear radiation. But after you're through cracking it, then you remove the rancid water, and it's a matter of a bunch of lawsuits what it is you're going to do with that rancid water. But you're going to put it in some place where it doesn't affect people, according to the companies. And then you pull out down the same pipe the natural gas coming out of the shell, and that is why gas prices have been going down. Okay, so what's involved in piezoelectricity? Mathematically, this is the thermodynamics. A shear will produce a polarization, and an electric field will produce a stress, and you can create mechanical energy, send it into electrical energy, and because we are theoretical physicists, we describe this as a phonon to photon conversion as a Feynman diagram, with the piezoelectric coefficient being at the vertex. If you're an engineer, then you say, if I squeeze the thing, I'll convert it to a voltage. So mechanical power is force times velocity, electrical power is voltage times current, and the engineering way of describing it is every bit as good as the Feynman diagram way of describing it. It's just that with theoretical training, we have a prejudice on which way we do the calculation. Then this is about tensile strength. This kind of earthquake, these rocks are brittle. So you just go up, and then you hit a point where you hit a critical strain, and then you fracture the rock. You've seen fractured rocks if you drove past mountains with rocks that have cracks. But these things called micro cracks, yes, I give a reference here if anybody wants it. This has nothing to do with us, but it's a very good article on understanding micro cracks. Before you get these big cracks, you get these little cracks and they move. When we published it, this is our picture of a little crack taken out of an elasticity book. And this is a picture of what it really looks like with a crack size of about 100 microns. And they move. And if you know Young's modulus, Poisson's ratio, surface tension, you can get the crack size, and you can get roughly the stress at which the rock is going to crumble. And I show here two articles. One is by Carpentieri and co-workers, whose lab we had visited, on neutron production within microcracks. This is by Sebastian, Wayne, and myself on why we think there are neutron production within microcracks. And we would say that it's electroweak interactions gotten by the electric fields. And this is the arithmetic by which we do some numerical estimates. And what's happening is the acoustic waves in the crack are coupled to the microwave waves in the crack, and the energy goes back and forth, and the microwaves accelerate the electrons, and they have a large effective mass. So we were happy to say this is what's happening, and you get very slow neutrons. Carpentieri informed us that they see some slow neutrons, but they also see fast neutrons at maybe 10 or 20 MeV. So the fast neutrons was outside of the scope of the theory that we had up to that point, because up to that point we should have gotten long wavelength neutrons, which I think has happened. But now there was this new process. Oh, this is another little graph taken from a Russian article, pointed out to us by Carpentieri. And in a region of Russia which I can't quite locate. The top graph is what is the energy of each earthquake they've seen over about a 10-year period. And the bottom part is what are the background neutron counts. And when you have a lot of high energy earthquakes, you have a lot of background neutron counts, and vice versa. So they more or less follow each other, which is another indication